Hello, I hope you are doing good again today. We're going to start Unit 8, which is on differential equations. It's Chapter 7 in our textbook. I would highly recommend that you take some of your own notes, whether you print off the blank copy that I provided on Canvas and fill those in, or just take your own notes on your own paper, or do it digitally, however you want. Instead of just watching the video, I highly recommend writing some stuff down. Not only can you use those materials to help you on the AP exam, but just the process of taking notes is good, helps us learn. So today's essential question: what are differential equations and how can we approximate their solutions? So here we go. A differential equation in x and y means a differential equation with x and y, is an equation that involves x, y, and derivatives of y. In the past, we have solved differential equations of the form y prime equals f of x and y double prime equals f of x. In other words, we've solved differential equations where we're given either the first or second derivative, and each of those equations were entirely functions in terms of x. And we solve them by integrating. Because a function y equals f of x is called a solution of a differential equation if that equation is satisfied when y and its derivatives are replaced by f of x and its derivatives. So basically the solution of a differential equation is just the original function y, or f of x. So here's an example. Example number 1. We want to show that y equals e to the negative 2x satisfies the differential equation y double prime plus y prime minus 2y equals 0. We want to show that this equation here makes this differential equation a true statement. It's a differential equation because it has y in it, it has a y prime in it, it has y double prime in it. It doesn't have any x in it, but that's okay. It doesn't have to have all those things, just some combination of them. So, to work with this differential equation over here, we need y. We're given y. We need to know what y prime is and what y double prime is. So, I'm just going to find them. So, y prime would be, well, we have to apply the chain rule, but the inside derivative is negative 2. So, we'd end up with negative 2 e to the negative 2x. That would be the first derivative. The e part, of course, remains the same. The second derivative, same idea, multiply the same thing but by the inside derivative, which is negative 2. We get positive 4 e to the negative 2x. Then we want to verify that when we plug those into the differential equation, it makes a true statement. So the differential equation has us plugging in y double prime first, which is 4 e to the negative 2x, plus y prime, which is negative 2 e to the negative 2x, minus 2 times y. And y is just the original y over here, which is e to the negative 2x. And we want to show that that equals 0. Well, this is just 4 e to the negative 2x minus 2 e to the negative 2x minus another 2 e to the negative 2x equals 0. The left side, we have 4 of these, minus 2, that's just 0 of them, equals 0, and we're good. So this equation right here would be a solution to this differential equation. Example 2. For the differential equation x times y prime minus 3y equals 0, verify that y equals c times x cubed, where c is a constant, is a solution of that differential equation, and then find the particular solution when y of negative 3 equals 2. So this is kind of like the previous problem. We want to show that this is a solution of the given differential equation. The c there is our constant of integration. We're used to seeing things like x cubed plus c. We always have plus c's whenever we've integrated before. But as you'll see in the future, is with some of these more complex differential equations, sometimes the c ends up in a different location than we're used to it being. And we'll end up with solutions like this, c times x cubed, instead of the traditional x cubed plus c. We don't need to worry today about how that happens. We'll get to that later. But the c is going to be all over the place in this unit. So we want to verify that it makes this differential equation right here a true statement. So this differential equation has x in it, x is just x, we have y, that's this y, and all we need is y prime. We don't need the second derivative, just the first derivative. So our y prime is going to be, just using the power rule, we'd bring down the 3, c is just a constant, so it's 3c times x squared, dropping the exponent by 1. Then we're going to plug everything into the differential equation. We're always going to write it in terms of x, simplify it in terms of x, excuse me. So the x that's already there stays there, times y prime. Well, y prime we just said is 3c times x squared, minus 3 times y was the cx cubed that we're given, equals 0. Simplifying, x times 3cx squared is just 3cx cubed, minus 3cx cubed equals 0. Obviously, if we take 3cx cubed minus 3cx squared, cx cubed, excuse me, we do get 0. So that is a true statement. It satisfies it. That means that this is a general, we call this a general solution. It has c in it. But now we want to find a particular solution that passes through this point right here. So we want a particular solution through that point. And writing y of negative 3 equals 2 is the same thing as writing f of negative 3 equals 2. So we want to take our general solution, y equals cx cubed. We're just going to solve for c. The y coordinate is 2 equals c times the x coordinate is negative 3 cubed. So 2 equals negative 3 cubed is negative 27 times c. If we divide, we get c is negative 2 divided by 27. Which means that our particular solution is really y equals negative 2 over 27 x cubed. So this is a particular equation that satisfies this differential equation up here, but also passes through the point that we're given. So now we're going to talk about slope fields, and this is really the big idea of this first section. So it says the family of curves that satisfies a differential equation of the form y prime equals f of x and y. So now we're not just looking at f of x's, functions that are written solely in terms of x, but the function could be written in terms of x and y variables, where f of x comma y is some expression in x and y. That family of curves can be represented by drawing a slope field. And that's what we have a picture over here on the right, a slope field. Sometimes some textbooks call it a direction field, but we'll call it a slope field. These drawings, these slope fields, can be used to visually approximate solutions to a differential equation. So over here, this slope field on the right is a visual approximation of all the potential antiderivatives, really, is what we're looking at. Let me give you an example based on something we already know. So let's say we were given the differential equation dy dx equals 1/2 x. To solve it, we would just need to be finding what y is. Well, we know the derivative is 1/2 x, and we just want y, so we're just going to integrate. If we take the antiderivative of 1/2 x, we get 1/4 x squared plus c. Just a basic antiderivative. So this is the general solution. Any equation of that form with any value of c would satisfy the derivative, the differential equation. And we can see all of our parabolas here. So we have we've got 1/4 x squared plus 0 right here in the middle, and then plus 1, and plus 2, and plus 3, and plus 4, and plus 5, and minus 1, and minus 2, and minus 3, and minus 4, and minus 5, all the way up and down, all the decimals, every number would work. All that plus c is just taking the parabola and shifting it up and down. This right here is what we call our family of curves. All these parabolas satisfy this differential equation. But it was easy for us because we could integrate. That was an easy derivative for us to take the antiderivative of, and so it was quite easy to solve that. A slope field is really nothing more than if we took these these solution curves and we just kind of dashed them, just looked at little sections of it and their slopes. That's all that's happening here. So, for example, that solution at 0 is really this solution right here at 0, and these slopes are kind of just showing us, giving us the general idea, if you just kind of connect the dots or follow the lines, the general idea of what a solution curve would look like. So we have it at 0, and then the one at 1 kind of, is right above it, and the one at 2, and so forth and so on. That's all a slope field is doing. However, we're about to look at differential equations that are not as easy to integrate. We'll eventually learn how to integrate some of them, but for now, they're not going to be ones you know how to integrate. So we're not going to be able to come up with this equation. We're going to learn how to draw these slope fields to give us visual, graphical approximations to what the antiderivative functions might look like. So let's look here at example 3. It says, consider the differential equation dy dx equals x plus 1 over y. First thing I want to point out is these types of differential equations will, as I've mentioned before, generally have both x and y in them. We can think of them as almost like the results of the types of derivatives we would get when we were using implicit differentiation. So a lot of times the antiderivative of these are going to be implicit equations with x and y in them. But for now, we're just going to approximate them visually using a slope field. So number 1 says, sketch a slope field for the given differential equation at the 12 points indicated. So there are 12 dots, you can see them, and we're going to sketch the slope field. And so the way we do that is we just plug each of those points in to the derivative equation. And it would help, probably is going to help most people to make a table. So I'm going to make a little table over here, where I have the point x comma y, and then dy dx. And I'm just going to start just up here at the top, at the point -1 comma 2. And all I do is I just take x equals -1 and y equals 2, and I just plug it in to dy dx. So -1 plus 1 is 0, divided by 2 is still 0, and so the slope at the point -1, 2 is 0. So to show that visually, at that point, we're just going to draw just a little line, a little slope line, almost like a little tangent line, and we're going to have a slope of 0. Well, a slope of 0 just means, horizontal, flat. So we just draw a little line that has a slope of 0 at that point. Now I'm going to move from left to right. So my next point over would be 0, comma 2. If I plug it into the differential equation, that's 0 plus 1, which is 1, divided by 2, that is 1/2. So right here at the y-intercept of 2, I need a slope of 1/2. Well, 1/2 would be up 1, would be going from here, we're going up 1 and over 2. You don't have to be exact with this stuff. You might want to use a little straight edge to help you, but 1/2 is going to be, you might have to kind of visually check it, kind of something like that. Moving over, the next point would be 1, comma 2. Plug that in to the differential equation. 1 plus 1 is 2, divided by 2 is 1. So right here, we want a slope of 1. That would be up 1 over 1, or down 1, left 1. It should be in line with the point right here at 1. That would be a slope of 1 going through this point right here. Should be steeper than the slope of 1/2 that we've just drawn. Next row, moving down, I'm looking at the point -1, comma 1. If I plug that in, I get a slope of 0 once again. So I'm just going to go ahead and draw that in. Moving over, the next point is 0, comma 1. That gives us a slope of 1. So it should be like that. It should kind of be in line with that other line that had a slope of 1 there, just coincidentally. And then we have the point 1, 1. If we plug 1, 1 in, we get a slope of 2. So 2 should be our steepest, up 2 over 1, or down 2 over 1. It should be almost look like it's connecting to this point down here if it has a slope of 2. So it's going to be kind of like that. That should be the steepest line that we've drawn so far. All right. I'm going to save some time here. I'm not going to draw, I'll just draw the other 6 in. These 2 points will also have slopes of 0 at -1, or at the y-intercept of -1, we'll have a slope of -1, which is like this. At the y-intercept of -2, we'll have a slope that's -1/2. It's going to be a little shallower, kind of like that. At the point 1, -1, it's going to be -2, so kind of like that. And at 1, -2, it's going to be -1, so like this. In fact, it looks just like the top half just reflected down in this particular case. Not every time, just in this case. So that's our slope field through those 12 points. Obviously, it's not nearly as detailed as the one I've shown you here on the top right on this slide, or on the right side. But we only did 12 points. So now we're going to do the second part. The second part says on the interval between -1 and 1, well, that's where our graph is, sketch the solution curve that passes through the point 0, -1. So we want to approximate what the antiderivative point or function would look like if we were to integrate this differential equation and have it go through the point 0, -1. So we start by plotting the point 0, -1. So that is this point right here. All right. And then we kind of ride the wave, is the phrase I use. As we move to the right, we just kind of follow the direction of the little slope line. So this one's definitely going here. This one's continuing to go that direction until we're off the screen, so we can do that. On the left side, we're also going up, but then we don't have a like a slope here. It's actually undefined because y is 0, so if you plug it in here, you get an undefined slope. But everywhere else in that column has a slope of 0. So we can see that as we approach x equals -1, all these solution curves are going to be flattening out. So we can kind of flatten it or show that we're starting to flatten. It's not a real exact science. It's just kind of a visual approximator. In other words, that solution curve isn't going to be a perfectly straight line. It is going to flatten out as we head towards the left endpoint at x equals -1. And that's just a visual approximation. All right, example 4. Sketch a slope field for y prime, or dy dx, equals x minus y for the 16 points indicated below. Then sketch the solution that passes through the point 0, 2. I would like you to try this problem. So if you want right now, go ahead and just pause the video and try it for these 16 points. There's none along the x-axis. We do have 4 points along the y-axis. If 16 is too many, maybe do 4 of them or 8 of them, just enough to get a little practice before continuing on. All right, I'm going to reveal the solution curve now. So I'm scrolling down here. So this is what that completed slope field should look like on the left side. If you drew them in, those are what the slope should approximately look like. They don't have to be like exact. No, I'm not going to get out a ruler and assess you on how perfect your slopes are. If this happened to be part of an AP question on the AP exam, they wouldn't get out a ruler. Generally, what we're looking for is slopes that are 0 should look flat. Slopes that are positive should be going up. Slopes that are negative should be going down. And just in general, steeper slopes with higher values should be steeper. Okay. On the right side, I've shown you a computer-generated slope field for the same differential equation. That's plotting more points. We just plotted kind of the unit points. This one plots like every quarter point, I think, or something like that. And you can just see the slope field come together with greater precision. So, second thing we want to do then is sketch a solution curve that passes through the point 0, 2. So we plot the point at 0, 2, which is right here. And there's nothing to the left, so we're just going to move to the right by following the curve. So the right edge of that line has us going down. So we head down, and then we get close to this line that's kind of flat. So we can touch it or not, whatever, but we're going to head flat and head this direction. And then the next line we're about to hit has us going up. So we kind of go up. And then this one kind of has us going up, but maybe kind of leveling out a little bit, something like that. And we have a solution curve that looks sort of like this. Now, before I move on, this is, like I've said, an inexact science. We're just creating a visual approximation to the antiderivative. So let me give you an example of an FRQ question that's been on a past AP exam. This is from the 2014 exam. They were given the slope field. So the slope field was already given in the problem, not the curves that you see drawn in, but the slope field was given to every student. And it asked them to sketch the solution curve through the point 0, 1. So on the first one is the correct answer. This is the answer straight out of the rubric. And then we have 3 actual student answers from the exam. And so the question is, which one or ones of these students' work received full credit? Notice they're all a little bit different. They all do go through the point 0, 1 as they should. We're told it goes through the point 0, 1. They all go through the point 0, 1, so that's a good thing. And generally on the right they go, kind of up and down. On the left they go down and then up, working backwards. But we can see that some go up more and some go down more and so forth and so on. And we can see how those compare to the actual correct answer. In actuality, all of these 3 students, A, B, and C, they all received full credit. They all rode the waves well. That's my little icon up there, ride the waves. They've got the general idea of what a solution curve would look like through that point. So everyone got full credit there. All right, one other thing we want to be able to do is match a slope field to a differential equation. So here I've given you a slope field, already created, and I am asking you which of the following differential equations it matches with. There's all sorts of strategies that you can use. I'll show you a few in a bit. But one of the primary ones is to look for where the slopes are 0. That's a good place to start. So I'm looking at the slope field and I see all these horizontal lines right here. Specifically, this is at y equals 1. I don't know if you can tell, but since we're going 3 in each direction, every one of these is actually at a half point. So we've got 0, 0.5, this is 1, then 1.52, 2.53. So all of these marks are going by increments of 0.5. So that's y equals 1. And we also have slopes of 0. It looks like they might just be tick marks on the axis, but they're not. We don't put tick marks on a slope field because it's confusing. We don't mark the axes that way. We try not to. And so at all of these values, this is everywhere where x equals 0. So every time x equals 0, we have a slope of 0. And every time y equals 1, we have a slope of 0. This is always a good thing to check first. So if we look over at the answer choices, A through E, every time we plug in x equals 0, we should get dy dx is 0. Every time we plug in y equals 1, we should get dy dx is 0. Those should give us slopes that are always 0. So if you do that, let's see. Well, I'm going to tell you the first 2. It's going to be a little easier if we kind of rewrite them in their factored form. So I'm going to factor out an x in the first one. If we factor out an x, we're left with y minus 1. And I will also factor out an x in the second one, and we're left with y plus 1. Okay. C doesn't factor, and D and E are already in their factored forms. So let's start with A. If we plug in x equals 0, 0 times anything is going to give us a slope of 0, so that's good. If we plug in y equals 1, 1 minus 1 gives us 0. If we plug in y minus 1 right here. And then 0 times any x coordinate is 0, so that's good. So this is a possibility. I'll put a question mark for now. If we look at the second one, and we plug in x equals 0, 0 times anything is going to be 0, so that's good. But if we plug in y equals 1, we get 1 plus 1 is 2. 2 times the x coordinate. Unless x is 0, you're not going to get a 0. So we need y equals 1 to be one of our zeros, so B doesn't work. In C's case, if we look at C, if we plug in y equals 1, we get 1 minus x squared. Well, unless x is 1 or -1, this isn't going to produce 0 for every x value. So that is also not a possible solution. However, if we look at D, if we plug in 1 for y, we get 0. If we plug in 0 for x, we're also going to get 0, so that's another possibility. Could be that one. If we look at E and we plug in y equals 1, we get 0. But if we plug in x equals 0, there is no x, so we wouldn't automatically get a slope of 0 every time x equals 0. For example, this point right here at the top, that's the point 0, 3. So the x is 0, but the y is 3. 3 minus 1 cubed is 8. That would indicate a slope of 8, not a slope of 0. I need a slope of 0 at that point. So this is not a possibility. So now it's either A or D. And there's all sorts of other strategies you could use. One way is just to start picking some other points. So I'm just going to cut to the chase. But let's say I pick this point right here. That is the point, what is that, -1, 2, I believe. Just say I picked that point. I don't know much about that slope, but I can see that the line's going down, so we must have a negative slope at that point. So if I plug it into A, I would have the x-coordinate, which is -1 times 2 minus 1, which is +1. -1 times +1 is -1, so that's a slope that's negative, so that could still be a possibility. If I plug it into D, the y-coordinate's 2, so 2 minus 1 is 1. And then I would take the x-coordinate, which is -1, and square it. Here, let me just show you this. So I'm doing 2 minus 1 times the x-coordinate squared. Well, this is 1. -1 squared is also 1, so this is going to give us a +1. We don't want a positive slope. We need a negative slope there, so it can't be that one, and by default it must be answer choice A. Those can be a little tricky. Those are more common, obviously, on the multiple choice questions on the exam, and you don't have any on the AP exam, so we won't necessarily work as much with those. But you'll have a little practice. Here's some other tips for reading slope fields. I already said the first one, look for places where the slope's 0. Number 2, look at the slopes along the x-axis when the y-coordinate is 0. Or 3, look at slopes along the y-axis when the x-coordinate is 0. 4 is look to see if the slopes only depend on x, like only an x is in the differential equation, or step 5, if they only depend on y, look for only a y in the differential equation. That would be like option E up here has only a y in it, which means the x's shouldn't impact the slopes in any way. Last is kind of what we did, the last thing we did, just pick some other points, maybe try points in different quadrants and just kind of check to see if the slope is reasonable, if it looks like it should be positive or negative, that sort of thing. All right, that's it. There will be an assignment posted. Have a nice day.